record it to the cloud just in case my computer crashes, which it's been known to do. I don't want to have to reshoot the entire thing, so we'll go from there. First things first, welcome back. Welcome to post fall break. I'm really jealous of y'all. When I was here as a student, we did not get a fall break. It was not something they allowed for us. It was just, hey, start in August and you get to leave again at Thanksgiving. So hopefully you guys took a couple of days off, got to relax a little bit, got to hang out. Before we get started on getting into regression a little bit deeper here, does anybody have any questions on the stuff that's outstanding right now? I know we've got homework 4 out, and then we've got the midterm out, right?
Yeah, I know some of them have already started working on the midterm. Looking now, several have started it. Had a couple already submitted.
So I'm gonna put a guilt trip. How many people have started it? How many people have at least looked at it? Yeah, let's make that number higher, please. So from that standpoint, let's make that number higher. For the simple fact that start early on these things. Like if there's one thing by the end of the semester you guys are going to figure out, especially y'all that are going to come hang out with me in 451, we like to start early on assignments. Okay, these things aren't overnight things anymore. All right, make sure you start early, make sure you put in the work. That also gives you time to ask questions. Now, here's my rule on questions, and I know this is Catherine's rule too. I will not give you an answer. That doesn't mean we won't talk about a similar problem. That doesn't mean I won't answer questions you have. Here is not a question. Hey, Brad, is this right? That's not a valid question, okay? Hey, Brad, I'm really struggling with this part. Can I talk through it with you? That is a valid question. Is this right is not a valid question. Can we all agree with that? Like, we all feel pretty comfortable about ourselves there? All right. Now, any other questions? Going once, going twice. All right, let me share my screen here and let's go to work for a little bit. You guys can see my screen, yeah?
Yep.
Awesome. Thank you, thank you, thank you. All right, let's go to work here for a little bit and let's pick up where we left off. So last time around, we were talking about putting lines through data, which we're going to call regression, right? As you guys remember, we go back up here. We say what we're looking at is a sample regression line. And all sample regression line is go back to your 8th grade algebra class, and what we were talking about was putting a line through data, right? We said there's a y-intercept, which we call A, slope, which we call B, and we said intercept is just the y-intercept. What is it? It's where x equals 0, or where the line crosses the y-axis in a plot, and B is just the slope. So if we looked at it, put this line through, A is just when x equals 0, so the x-axis, y-axis. It's when x equals 0, so when we're crossing the y-axis. And B is just the slope of the line. Slope of the line, the way I learned it, probably the same way you all learned it, because math is just so innovative, is rise over run. It's if we move right, how much did the line go up or down, right? So real simple concept. Why are we talking about it like it's hard? Because when you start using data, it ain't easy. All right. I ain't gonna say it's hard. It's just not easy anymore. And let me show you why. How do we find A and B? How do we find a slope and an intercept when I have a bunch of data points? These 3 plots have the same data points in it. Out of the 3, I want to go left, middle, right. Which line do you think fits the data better? The left one, the middle one, the right one?
I think it's got to be the right.
All right, so we're going with the right one. Everybody can agree it's the right one. Anybody going with the left one? Anybody going with the middle one? All right, post-fall break, everybody's on the same page. I like it. This is a great way to start. Now, here we go. Here's the more important question. Why the right one? Everybody agrees it's the right one. Why? Chris, go ahead.
Because it has, like, the line goes to the middle, and it has equal distribution on upside and the downside.
All right, there's 2 major points there, and we're going to hit these topics. One, it goes through the middle of the data. When we say middle, mentally, you guys see that positive trend, right? That positive trend. Everybody knows what positive trend was because everybody paid attention, what, 2 lectures ago? So we know that's a positive trend. We see it go through the middle of the positive trend. It goes through the center. There's as many data points to the left as there are to the right. When we say it goes through the middle, that kind of goes through the middle of the data, but it doesn't reflect the trend. Would everybody agree with that statement? Like it just cuts the plot in middle. Great. Awesome. This, we all agree that's just bad. Yeah, everybody's good with the thing on the left just being awful, and we're just not going to think about it anymore. The thing in the middle, yeah, okay, it goes through the middle, but it doesn't follow the trend. This splits the trend evenly. All right, so I really like that definition of it. It splits the trend evenly. Think of it as it averages out the trend. Would you guys agree with that statement? It averages out the trend. That's the way I want you to think about this for a second, okay? Now, we're going to start putting some definitions on things, and these are really important definitions, all right? So I'm going to make my hand flashy thing or do whatever you guys need to see from me, okay? I know, total dad joke at this point, and I'm going to keep doing it because it is one of those things when you guys are scanning through videos, I want you to stop and look at it, okay? Because there are important things that we're going to hit over and over again, and this is one of them. The definition is residual, okay? A residual. If I just say residual in any common day use, what does it mean? What's the word residual mean? Not in a stats context.
Byproduct.
Byproduct, leftover, right? I like leftover. The reason I like leftover is because it fits the stats definition too. All right, it's what's left over. So a residual is the prediction error for an observation. Think of your line as a prediction. We're going to say the line is what happens on average. All right. Now, if the line's what happens on average, let me pull this down just a little bit here. Where'd I go? And let me pull out my marker. The line is the prediction, okay? The line is the prediction. That's what I want you thinking about. The line is the prediction. The residual is the distance from the data to the line, okay? It's how much did I miss by? The whole point of a regression line is it puts a prediction on it. So when we put this line in, that's a prediction. The residual is the difference between the data and the line. That's all this says. It's the difference between y and y hat. Now, remember what y hat is. Y hat is just the outcome of our line for any value of x, okay? Residual, distance or the difference between your data and your line. How much did I miss by? You guys with me on that? Now, in regression and in prediction, go ahead and start thinking about something. It's not how right are you. It's how wrong are you. You are never going to predict perfectly. If you ever predict perfectly, your model's wrong. Deal with it. I'll show you why it's wrong later. When you fit regression models, the question is how wrong are you and how can we minimize the amount of wrong? All right. The residual is the quantification of how wrong you are. All right. Now, a few things. You can't switch the order of y and y hat in the formula. It's all y minus y hat. What does it mean when the residual is 0? It means you're not wrong at all, right? It means your line and your data are the exact same thing. Would you guys agree with that statement? If the residual is 0, it means y is equal to y hat. What's that mean? It means the data points are right on the line. Y'all good with that? All right. What does it mean if the residual is less than 0? If the residual is less than 0, it means that quantity is less than 0. It means the data points below the line, right? Y minus y hat being negative, it means y hat's bigger. If it's positive, it means y hat's smaller. That's all it means. It just tells you where you missed at. Now, here's our goal. We're going to choose A and B so that the residuals are small and we're not systematically over or under predicting the true value. So what we're going to do, y'all always hear the statement, why did I take calculus? I've never used it in real life. You know, everybody likes to talk about, I've never used that math class in real life. Well, you guys are getting ready to start using every math class you've ever had in real life, okay? When we're building forecasting models, when we're building predictions, what we're actually doing is we're minimizing functions. For those of you guys who just got through calc and didn't really pay attention and thought this is absolutely useless, why are they making me take this? Let me give you a reason. One of the things we have to figure out how to do is minimize functions. Minimize means take the derivative, set it equal to 0, and solve. Okay. Now, this ain't a calc class. I'm not making you redo calculus in this class. That's a waste of your time. But what I want you to understand is everything we do from here on out has calculus underpinnings in it. Y'all good with that? So here's my goal. I need small residuals. I want my predictions to be good. I don't want to be over or under. Would you guys agree with me that that is an over prediction at almost all times? All the data is under the line, right? We don't want that. That splits it in half, but doesn't follow the trend. We don't want that. The question is, how do we get this? Well, what we're going to do is minimize what's called the residual sum of squares, or RSS. Okay? RSS. The residual sum of squares is one measure of how well a regression line predicts values of the response variable. It is literally the sum of squared residuals. Statisticians are real creative, y'all, especially with how we name things. Residual squared sum. Residual sum of squares. You guys with me on that? All we're doing is we are taking the sum of y minus y hat, actual data minus the line, squaring it. Now, the first thing you guys are going to say is, why do we square it? There's 3 different reasons. I'm going to give you the non-mathematical one first, give you the second, and completely ignore the third. All right? The first one. If I tell you I'm 5 miles from someplace, does it matter whether I'm 5 miles north or 5 miles south? Or is it the fact that I'm 5 miles that matters to you? It's the fact I'm 5 miles. Distance is distance, right? By squaring this, what we do is we take it to distance. I don't care if I'm above or below. I care that I'm wrong. You guys with me on that? The second one, take a look at this. If I would replace that with X and X bar, that looks like the numerator of the variance, right? What we're really trying to do is minimize the variance of the residuals. That's the mathematical piece. And the third one, you don't care about yet. We'll care about it in 2 weeks. We're not going to care about it right now. So the first one, what's squaring it do? It makes it a distance function. It means if I'm above or below, I still missed. That's bad. Mathematically, it says what we're trying to do is we're trying to deal with the variance of the residuals, okay? We're trying to deal with the variance of the residuals. Why is that a variance? Because if I look at that normally like any other equation, X minus X bar is the variance. Now, what you guys are going to figure out here in a minute is this Y hat is actually a mean. Remember we said it goes through the average? It's actually a mean. All right. Krish, what's up?
I had a quick question. I think it might be a little too early to ask. With this, the whole formulas and stuff, do we run through R when
Oh,
we
yeah.
work on
You guys aren't doing this by hand. Right now, all we're doing is getting a conceptual feel of regression.
it? Because
When
that's
it's
one of
time-
my, yeah, go
Sorry.
ahead.
Go ahead.
Now, I was saying that's one of my fears because I'm not like, I don't want to deal with the calculators.
Oh, no,
Business.
you're, trust me, when we get to that point, there'll be enough R for everybody. I promise. You
Yeah,
guys I'm going to wear you out with it. But for
Some
right now, I need
calculators
you
are
to understand
compatible.
why we're doing it.
Yeah, because some calculators are compatible, some are not, and I just don't want to deal with it.
You're never doing this on a calculator.
Okay, thank you.
You're never doing this on a calculator. Trust me. You're doing this in R with data. Right now, I need you to understand the basic concepts before we can do anything else. Because if I have you just interpreting code, you ain't ever going to be able to do this in practice. Okay. Now, next piece. We want to minimize this. Okay. We want to minimize this. We want to minimize the residual sum of squares. How do we do that? We develop what's called the least squares line. And here's the equation. And to Krish's point, this is what R or any other programming language does for you in the background. It calculates this B, your slope, which is just the correlation coefficient R times the standard deviation of Y divided by the standard deviation of X. Now, you can do this on your TI-83. It is a waste of your time. You know how I feel about you guys calculation standard deviation variances by hand. The intercept is just the mean of y subtracted from the mean, or excuse me, the slope coefficient times the mean of x. There's nothing that isn't introstat in calculating regression coefficients for what we call simple linear regression. Simple linear regression, okay? Simple linear regression. Simple doesn't mean easy. Simple means a single predictor variable. All right. Now, this is the equation. Ooh, ah, great. But the whole point of it is, how do we get this least squares line? We minimize the residual sum of squares. That's your takeaway from this. I ain't walking through the math. It's calculus. It's first derivative, set it equal to 0, solve a problem. It would have been a heck of a question on a calc final. It ain't for us, though. How do I get the least squares line? I minimize the residual sum of squares. Let me say it one more time. How do I get the least squares line? I minimize the residual sum of squares. What's the residual sum of squares? Look, all we're trying to do with the residual sum of squares is just put a distance metric on the residual. We're trying to minimize the variance of the residuals. That's what you take away from this first part. Y'all with me? Why are we doing it? To get the best line we possibly can. You guys with me there? All right, next piece. Here's some properties of OLS, or the least squares regression line, LSL is another way to say it. Changing X and Y around will give you a different regression line. Well, no kidding. That should be the most obvious thing on the planet, right? How do we talk about these things? One is an independent variable, one is a dependent variable, right? We think one drives the other, or should drive the other. That's the question. Some residuals are positive, some residuals are negative, but this statement is always true. Notice that is not squared. The sum of the residuals from the least squares regression line will always add to 0. Mathematical fact, great for a Jeopardy question, but all it's telling you is it's trying to find the average line. That's what it tells us. You guys with me on that? Number 3, the residual sum of squares for least squares is smaller than any other line. This is a mathematical fact. Useful in practice? No, but it's a mathematical fact, so we bring it up for like 2 seconds. The least squares line always goes through the average X and average Y. It has to. Mathematical fact by this right here. Guarantees it. Now, there's 3 things you need to hear about this next part, and I need you to hear it now. R squared, the correlation squared, provides a measure of how well the least squares line describes a relationship between X and Y. If correlation describes the linear relationship, R squared provides a different measure. Correlation squared, that's all I'm saying. R squared, what it actually is the proportion of variation in Y that is explained by its linear relationship with X. Basically, how much of the variability in Y can I explain by just knowing X? That's all it is. You'll hear this talked about in layman's terms as an R squared value. I told you, we're really good at naming stuff. Correlation is R. What's this thing? R squared. Okay. It is common practice to use. By the end of this class, you'll figure out why it's complete garbage in a lot of ways. But for right now, to teach you why it's garbage, I need you to understand what it is. Y'all with me on that? It's correlation squared. We know correlation isn't the best metric on the planet anyway, right? Why? We talked about it last time. It can't deal with quadratics. It's a straight line relationship. Y'all with me there? The closer R squared is to 1, the better X can be used to predict Y. If R squared equals 1, all the variability in Y is explained by its linear relationship with X. Basically what it does, and this is what correlation does, right? It talks about the strength of a relationship. You guys agree with me there? That's what correlation did. Talked about the strength of the relationship around a straight line. R squared just quantifies something. This interpretation of it right here is one of the biggest takeaways from this. R squared is just the proportion of variability in Y explained by X. Go back to the original thing we talked about in this, when we talked about the movie example, right? We talked about production costs versus box office revenue, right? What if I could tell you I could explain 90% of changes in box office revenue by just knowing the production cost of a new movie? That makes it a really easy investment, right? Now, what if I can tell you I can only explain 20%? It gives me some insight, but not a ton, right? So that statement right there, that's a confidence statement. It's how much can I explain? And we'll come back to this and we'll hit this over and over and over and over. Okay. Right now, all I'm doing is planting the language in your all's head, because we're going to revisit all of these topics, especially from a code standpoint and an interpretation standpoint. Y'all with me on that? So again, we're just putting some definitions on words. Now, we'll come back to all this. Let's talk about, actually, no, I don't want to skip over that. I apologize. Let's talk about this 200-meter dash example we did a little bit ago. So what we're interested in is quantifying the linear relationship between Olympic winning time of the 200-meter dash and the year which the Olympics took place. Let X be the year, Y be the time. All right. Now, we'll come back and we'll talk about this code, but here's what I want you to understand. This right here, this is my intercept, and this is my slope. So here's how I interpret this. And we're going to review this over and over and over again. What we're saying right now is at year 0, the intercept is 22.355. Now remember, year 0 in this case was 1900. For every 1 year increase, on average, I will see times decrease by 0.03 seconds. That's all this says. So the line itself is Y equals 22 minus 0.03 times X. That's all the line is. Now, this is the way R formats it. When you see this, and you'll see a bunch of output like this as we go. I'll teach the output a different day. But what I want you to understand is here's what we're getting back. That's the line we're getting back from R. So let's start there. Use the R output to find the equation of the least squares regression line. Great. Interpret the value of the slope. Now think about this. What we're going to say, think about just this equation right here. This is the importance of regression. If X goes up by 1, what do we expect Y to do? And I'm going to put the hat on there to say it's the line. We expect Y to decrease, right? If I take Y from 0 to 1, how much does it go down? By 0.03, right? Y'all with me on that? Plug a 0 in right here. Becomes 22, right? Plug a 1 in right there. It becomes 22 minus 0.03. Everybody agree with that statement? So the difference is it goes down by 0.03. So when we talk about a slope coefficient, here's what we say. Listen to how I word this. If we increase X by 1 unit, on average, Y goes up or down by the slope. In this case, we say it goes down because there's a negative sign, right? So what we're going to say is, on average, 200-meter dash times improve, in this case, decrease by 0.03 seconds every year. You guys agree with that statement? That's what that line's telling me? All right. How much would we expect the 200-meter dash time to improve from one Olympics to the other? 4 times that negative 0.03, right? We see a minus 0.03 or a 0.03 decrease every year, multiply it by 4. We'd expect the winning time to be about 0.12 seconds faster each Olympics, right? Now, operationalizing this, that helps us train. If I know what time I have to beat to win an Olympic gold, that helps me try and meet that time, right? If I'm targeted in on that time, here's what can happen. We can plug other values into that line. Estimate what the winning dash time might have been had the Olympics been held in 1950. Plug a 50 in, do a prediction. All right. Now, we can calculate R squared values, which we'll talk about more, but it's just hiding out right here. R squared, what this says is 90% of the variability in the response, so in your time, can be explained by what year it is. That's pretty good. We can calculate a correlation off that. We can do a lot of things. All right. Here's what that line looks like. We'll go through all this code later. We're going to come back and hit this. This is the intro stat version of this. We're going to spend the rest of this week doing the advanced stat version of it. But right now, I have to get you all on the same page with me. You guys with me on that? Now, let's talk about how we use this a little bit. Regression analysis is something that's a little bit different than regression. Regression is just about fitting the line. I told you there's two reasons we fit this line: prediction or inference. Okay. From a prediction standpoint, fit the line, make a prediction, you're good. From an inference standpoint, we got to understand this next part. All right. We've learned how to explore and describe the observed relationship between two variables for sample data. In other words, we have learned how to describe some data that's sitting in front of us. In the remainder of this section, what we're going to do is we're going to talk about how to use these sample statistics to make inferences about true relationships. Okay. So what we do is we say the actual relationship in this data is this. Sure. Thank you. Is that better? Awesome. Now, what we're saying is the real relationship. Notice there's no hat on this thing. The actual value is equal to alpha plus beta x plus this epsilon. What I want you to think about here is alpha is the true population intercept, beta is the true population slope, and epsilon's the scatter. It's the part we can't explain. I want you to think about this as what's in the box is your line. What's in the circle or the weird circle or whatever I just created there is the leftover. It's the residual. You guys with me on that? That's if we knew every possible data point ever. A and B, that's different. A and B, that's what I calculate from my data. Alpha and beta, that's what I calculate from the population level. You guys with me on that? Now, just a reminder, what's the difference between a population parameter and a sample statistic? Sample statistic is calculated from our data. A population parameter is what the truth would be for the entire population that we never observe. Y'all with me there? So the whole point of inference is how do we take the sample statistic and infer it about the larger population? Y'all good with that? All right, let's go to work a little bit on it then. Now, you're going to see this concept show up. The line itself, which is this alpha plus beta times x, that's just the average. Remember what we talked about way up here? We said that looks like it goes through the average of the data points. Same concept here. Same concept here. Y'all good with that? What we're doing is we're saying that line is just the average. It's our estimated average. It's the average value of y as x moves. So as we change x from here to here, what we're saying is the average y for this value of x falls on the line right there. The average y for this value of x falls on the line right there. Pretty straightforward, right? Now, how are we going to make this work for us? We have some assumptions because what we're going to do is we're going to work on the mean. We're going to work on the mean and we're going to work on the trend. So we forget this epsilon exists just to say, hey, look, we can't explain that part. We focus on alpha and beta. Here are our modeling assumptions, and these are really important. You're going to hear them over and over and over again. First one, the linear relationship is appropriate. This ain't a curve. Seems like it'd be a pretty bad idea to fit a curve with a straight line. Everybody agree with that? You would be shocked how many people do it though. 2, normality. The distribution of the y values at any given value of x is normal. Let me show you a picture of what that means. What it talks about is the spread around the line at all these different values of x. What it says is when we condition on x, when we condition in this case on what year it is, the data is distributed normally around the line. Okay. Now, what's that say? It says there's a good fit. All right. We'll come back to ways to test for that, talk about that, and think about that. All right. It's an assumption for right now. We're going to assume it works. Last piece. Constant variance. The standard deviation of y sigma is the same for all values of y. Basically, what it says is these vertical lines I'm drawing that talk about the spread of the data are all the same height. If they're not, we got problems. I'll show you how to recognize that. Basically, what you don't want to see is something where your data looks like a megaphone. And it's really common in practice. I want you to think of portfolio growth. I want you to think of customer spend relative to time they're a customer. Think about how things change. Just think about height curves for a second. Like just human growth curves. That's something everybody can explain. I want you to think the difference of a ½ an inch in height for 5-year-olds compared to a ½ an inch in height for 22-year-olds. One's a lot closer to us than the other, right? Difference in ½ an inch height when somebody's only 36 inches tall feels like a lot, right? When you talk about somebody who's 72 inches tall, it's a big difference. You guys agree with that? Just something to think about as you go here. Now, those are assumptions that we're going to assume are met for the moment. I'm going to teach you how to check them later. Now, what we're going to do is we're going to make inference about the population regression model. All right. This is just, we can do confidence intervals and hypothesis tests. All right. Now, the idea is to use A and B to talk about alpha and to talk about beta. You know how we use the sample mean to talk about the population mean? We're going to use the sample line to talk about the population line. Does that work for y'all? It's not a huge jump. Use sample, talk about population. Welcome to stats. Like that's all it is. How do we use the data to inform a population model? All right. Now, there's a couple things you're going to see. The intercept and the slope just become estimates of alpha and beta. We can make predictions the same way. All right. But what I really want to get to is this. What I really want to get to is hypothesis testing and why it matters. Most of the interesting information about the linear relationship between two quantitative variables is captured by the slope of the population regression line, beta. Therefore, we will focus on making inferences about beta. We can also construct hypothesis tests and confidence intervals for the intercept alpha in a similar fashion. However, recall from what you should have covered in your intro stat class, that is not always reasonable to interpret alpha in the context of the problem. A lot of times we don't have data at 0, so it's just something that helps the line. What we actually care about is the slope. And what I actually care about is one value of the slope. That slope is positive. That slope is negative. You guys agree with me there? If I have a positive slope or a negative slope, there is a relationship between the two variables, right? What would the slope be if there was not a relationship between the two variables? Positive relationship, right? Negative relationship, right? What relationship?
No relationship.
There we go. I like it. Now, if we have no relationship, what's the slope coefficient?
0.
There it is. The thing we care about. And the biggest question in statistics. Does the slope coefficient equal 0? You guys always got, in your intro stat class, you would test, does the mean equal, like, is the mean equal to 75? Who cares? This one's one that matters because what it allows me to do is say, is there a relationship? If there's a relationship, what we say is it's useful information in help explaining one. It help using one variable to explain the other. If there's not, throw it out. It's noise. Have you guys ever heard the phrasing, there's signal to noise, right? Trying to detect signal from the noise. That's what we're trying to do here. We're trying to say, based on the variability in this data, is this useful information? Does it help us understand? If not, throw it away. It's not worth it. Y'all with me there? All right. This right here is the entire ballgame for inference. Now, here's what we use. Sample slope is the point estimate of the population slope. Nothing crazy. We can calculate a standard error. R does that for us. I'm not highlighting how you calculate the standard error of a slope coefficient, not in an undergrad class. Barely do it in a master's level course. It's tough. How many of you guys have taken 2 semesters of linear algebra? Then it wouldn't be worth it anyway to even have the discussion. Understand software is going to give this to you, okay? What it's going to do, and we're going to get into some of the complexities of this. What it's going to do is it's going to give us a variability calculation, all right? But this is the biggest thing. Remember, we talked about sampling distributions. Sampling distributions are how the sample statistic varies from sample to sample. It follows a t distribution. Now, you guys remember what a t distribution is? Normal distribution's bell-shaped, right? Symmetric. T distribution's actually real interesting. Call that a normal distribution. We're going to try drawing that one more time. I need to invest in an iPad where I can just draw this stuff. This will work. I want you to think the t distribution is that second line. It's that top line. Okay. Normal distribution has this nice property. Think of it as a baseline. T distribution has degrees of freedom. What it does is it puts more probability in the tails. It's what I'm going to call fat tails. Okay. See how this is the area under the curve and this is the probability that would come from a normal distribution? See how it's much higher for a t distribution? What it does is it ties it to the number of observations minus the number of parameters we're estimating. We're estimating an intercept and a slope. So there's 2, n minus 2. What it does, it places a weight, places value on how much information you actually have. If you have a small sample, there'll be much bigger tails. If you have a large sample, what it actually does is it converges to a normal distribution. You will never have to find this p-value by hand. The last time you will actually ever remember it's a t distribution is probably right now, but you can't say I didn't tell you. You guys with me on that? That is something you should hear 2 or 3 times. You'll hear it again. But what you're going to figure out is R and all this software tests this stuff for us. What we need to understand is what it's doing. It is testing that. It is asking the question, is the slope coefficient 0? You guys with me on that? There's all this statistical theory that makes it work. That is introductory statistical theory. All right. that is introductory statistical theory. When I say statistical theory, you cover it, the concept in an intro stat class. But for our purposes, what we actually care about is that it works. Now, we're going to have confidence intervals. Confidence intervals just says, here's my range of values. Confidence interval, you'll remember from your intro stat class, I'm 95% confident that the true parameter falls in this range, and we're going to have a lower bound and an upper bound. If we're concerned about the slope coefficient, what's the only value we concern ourselves with? 0. If 0 is in that range, it says it can be both positive or negative. And if it can be both positive and negative, that means 0 is an option. You guys agree with me there? And if your slope can be 0, that means the variable is unimportant. Fair enough? The other thing this allows you to do is quantify growth. So go back to our 200-meter dash example. Well, actually, that slope coefficient is between 0.1 and 0.2, which means you're going to see a drop of 0.1 to 0.2 seconds. Okay. Now, hypothesis test. How many of you guys remember what a p-value is? All right, help me out.
Is that the probability?
It's a probability statement.
All right.
Right on with that. But what is it? It's a probability, but it's a probability of what?
Isn't it the probability of like something occurring, like the probability that it will occur?
Sorta. Anybody else got an idea here? Nothing you guys have said is wrong yet. So let's feel good about that. But do we need to have an honest conversation about what hypothesis testing and p-values are? You guys want that reminder? I need thumbs up if your video is not on.
Is it normal probability?
It's not just a normal probability. Let's talk about this for a second, because this one's important now. You guys are scaring me a little bit. So we're going to take a step back. We're going to slow down for a second. Okay. Hypothesis test. We have a null and alternative hypothesis. Do you guys agree with that statement? Let me give you some quick, just reminders of what null and alternative hypotheses are. A null is always going to have an equal sign in. It's going to have an equals, less than or equals, greater than or equals. You guys with me on that? Alternative is the other thing. If our null has an equals, it has a not equals. If our null is a greater than or equal to, it'll be a less than. If our null is a less than or equal to, it'll be a greater than. Would you guys agree everything I've got boxed here is an opposite? Let me go ahead and delete that and actually draw a thick line. So equal, not equal, greater than or equal, less than or equal, greater than. Does everybody agree those are opposites of each other? All right. So we make a null hypothesis. All right. Since the null hypothesis always has an equal sign in it. All right. Since the null hypothesis always has an equal sign in it, we're testing the hypothesis that beta equals 0, beta not equals 0. I'll walk you through the example of the regression case. Okay. Beta equals 0, beta not equals 0. If beta equals to 0, there's no relationship, right? If beta doesn't equal 0, there is a relationship. We don't care whether it's positive or negative. One exists. Does everybody agree with that statement? All right. So what we're going to do is we're going to say the null hypothesis has an equal sign in it. That's beta equal to 0. All right. Alternative is not equal to 0. Now, when we're testing hypotheses, what we do is we assume the null hypothesis is true. And we test under that. You guys with me on that? Assume innocent until proven guilty, right? Think of it that way. Assume the null hypothesis is true. Assume there's no relationship. The whole point of a hypothesis test is to quantify this statement. What's the probability I would observe my data or something more extreme given the null hypothesis is true? How reasonable is it that I would observe my data, my regression coefficient, given the null hypothesis is true? So what we're trying to either disprove the null hypothesis. We're not trying to prove the null hypothesis. We're trying to disprove it. You guys with me on that statement? So what we do is we come down here and we say, look, we know this thing has this sampling distribution. And Brad's going to draw one of his ugly normal distributions. And guys, it don't get much better if I'm in a classroom on a chalkboard. So I apologize about that. Kristen can verify that because she's watched me draw this ugly stuff on a board and it don't get pretty. What we do is we say, look, this thing is centered at 0. Let's say this is where my regression coefficient comes out. We run a regression model. This is the B I get. What we're asking is what's the probability I observe this B or something bigger than this B, okay? That's what the p-value is. Now, if I tell you, I don't want to go through the math for a second. I just want to talk about a p-value definition. P-value comes from this test statistic, and that's great, and that's awesome. A p-value, by definition, is the probability I observe my statistic or something bigger, more extreme, given the null hypothesis is true. If I tell you I have a p-value of 0.0001, what that's saying is the probability I would observe my regression coefficient or something bigger than it is 0.0001. When we ask, do you reject or fail to reject the null hypothesis? What we're asking is that number small enough for you to basically say, look, no, my data didn't come from that distribution. Assume the null hypothesis is true. Assume your data came from a distribution where the true regression coefficient is 0. Then disprove it. P-value 0.0001. That is less than 1%. Does everybody agree with that statement? At that point, I'd be saying there is less than 1% chance my data came from the distribution where the slope coefficient equals 0. So I'd reject the null hypothesis. I'd say, look, that's improbable. Not impossible, but it's not a high enough probability for me to say it occurred. I reject the null hypothesis. Slope coefficient is not equal to 0. That's what a p-value is. Now, you guys are used to comparing it to 0.05. Is my p-value less than 0.05? Right? You guys have done that. All you do is you check and you ask the question, is that less than 0.05? What it's telling you is you're going to reject your level of confidence. You need to reject the thing that makes you feel certainty is 5%. If the probability is less than 5%, you're going to say it's improbable and you're going to move on. You're going to reject the null. You guys know why we use 5%? The first textbook example ever written on the topic was 5%. So everybody used it because they thought it was gold. Do you know why they used 5%? R.A. Fisher was the first person to ever do it. R.A. Fisher has his flaws as a human being, but he is known as the father of statistics, and we recognize him that way. Now, if you Google him, you figure out what he's about. Do not agree with a lot of that stuff, but he's the first person who wrote it, so we're going to cite it that way. Looked down on his hand and had 5 fingers. That's why he chose 5%. Most of modern statistical theory had been written around because somebody had 5 fingers. I told you, we're all real creative in this stuff, right? Now, what we want to come back to is this one topic and this one concept. When we reject a null hypothesis, when we calculate a p-value, all we're asking is what's the probability that null hypothesis is true and I observe my data. If it's small, we reject. If it's big enough, we fail to reject. That's it. We'll pick it up here next time, and then we'll start getting into some coding and some advanced stuff. All right. Guys, have a great week. Let us know if you need anything. Let us know how we can help you. Okay. Stay safe, stay healthy.